Dear friends, very welcome to the House of Sweden and the Embassy of Sweden. And to participate in an event hosted by the Embassy as part of their preparation for the journey to Stockholm to receive the Nobel Prizes. I would say that this has become a yearly tradition since the United States, more often than not, receives a handful of Nobel Prize laureates each year. And this is, of course, a true testament to the outstanding research powerhouse that the United States is. I think actually it's almost, not a record, but almost a record. There are 8 American laureates this year. I think the record has been 11, but so 8 is quite remarkable still, so congratulations to that. There are actually an outstanding 372 US Nobel laureates to date, and the Nobel Prize was instituted in 1901, so it's quite a while. And there are more Nobel Prize laureates than there are days in a year, and I think that's quite something. Sweden actually just reaches the month of the year. We have 31 laureates, which is maybe not so bad, given that we are not a very large country. So this afternoon, 6 out of 8 of the 2017 laureates are here. And you have all done amazing things in physics, chemistry, physiology, or medicine, and economics. So in physics, we have Professor Rainer Weiss. We have Professor Kip S. Thorne. And we have Professor Barish, who could not attend today's symposium. In chemistry, we have Professor Joachim Frank. Physiology or medicine, we have Professor Michael Rosbash, Professor Michael W. Young, and Professor Emeritus Jeffrey C. Hall, who could also, unfortunately, not attend today. And then we have the Swedish Riksbank Prize in Economic Science in the memory of Alfred Nobel. That is for Professor Richard H. Thaler. So welcome, all of you, and congratulations. I will not even attempt to try to explain the different theories of the laureates present, so I will leave that up to you, laureates, to do your best, at least to give us some insight during the talk we will have today. I do, however, want to congratulate each and every one of you laureates, and also your families and friends who have been so supporting during the long hours and years of research. It usually takes, just to put this in a picture of how the effort you have to put in to reach a Nobel Prize. You usually need to work for at least 20 plus years and then have a little bit of luck to sit in these chairs today. And you know, normally we say that it takes 10,000 hours to really champion a task. But if you calculate that in years, that's only 4.8 years if you put in 10,000 hours. So now you know what these men, the effort they have put in to be where they are today. I also know that you love doing research, and by that help human mankind. So really thank you all for that. And I really hope that you will use your new world-famous status to follow laureate Dr. Albert Einstein, who when asked on how he would use his fame, he said that it's a solemn trust to be used for the common good. So I really hope you will take his advice and do as he did for our common good. You have already done enough. and a lot, but that's very important. So with those few words, again, warmly welcome to today's symposium, and I will hand over the floor to Mr. Leish, our moderator for today. Very welcome. And also, you know, diplomats come and go in this town, but Alan Leish is a constant moderator of our symposium, so I think it's the 10th time.
Something like
yes,
that.
More than welcome.
Thank you. Thank you. Wow, good turnout today. All right. I'm still Alan Leshner. I'm known as the CEO Emeritus of the American Association for the Advancement of Science. And this is actually my favorite sort of public thing that I do because, first of all, it's a wonderful event. It's a great honor for them, but it's also a great honor for us because they've made significant contributions. Luckily, they don't know yet how great an honor it is for us, and therefore they're all delightful. I couldn't control myself, I apologize. My job is relatively easy. I also will not try to explain what they've done, but I will ask them to do that. The drill for today is going to be, I'll ask them each in turn to say a few minutes about what they did and why you should care about it and why it actually matters. And then we're going to open it up to questions. And I would like to explain two ground rules to you. One is, this is the most beautiful spot in Washington and the most distracting place to try to attend and listen. So I would ask that everybody now take a moment, look that way, admire the view, and try not to do it constantly during the event. There'll be birds periodically, but there's nothing, they're just birds. The second thing is, during the question period, I just would like to remind you that, so you know what a question is. A question is short. It does not have a long preamble. Your voice goes up at the end. Got it? Okay, no speeches. They're the speakers, you're the questioners. All right, everybody got it? So this should be a great deal of fun and very interesting. You can be thinking of your questions. We'll go through everybody and then we'll pass, I think we have a microphone, we'll pass that around. I will ask you, out of deference to my hearing, that you speak loudly and clearly and short. Okay, please. You are on.
I'm on. Oh, my God.
You're on.
Already. Well, I'm Ray Weiss, and Kip is my buddy, and we're going to be talking about gravitational waves a little bit. Let me quickly get you into it. There was a lovely theory of gravitation that was invented by Albert Einstein back in 1915, and it added some things to our whole thinking about gravity, which Kip will describe better to you. But what I want to tell you about is that it had something in it which was called gravitational waves. And the reason why that was essential was there was no way anymore that you could have action at a distance without having a time delay between an action here and something happening over there. Once Einstein had developed special relativity, the fastest that something could move was any ideas, any concept could move was with the speed of light. And that was not in the Newton theory at all, the Newton theory that you learned in high school. So gravitational waves are part of this theory, and it's a geometricized theory. I won't go into that. But what do they do, so you know, so you can imagine with me what we built so that we could detect these things. What they are they travel at the velocity of light. Let's say they move toward you. And what they do is they stretch space in one dimension, this way, at the same time as they compress space in a perpendicular dimension. That goes on for a bit, and a little bit later, it goes the other way around. This side, this gets compressed, and that gets expanded. And it keeps doing that as it travels along with the velocity of light. It's pretty straightforward. It is.
Sounds easy to me.
Okay. Now, the things that make gravitational waves are accelerating masses. The things that make electromagnetic waves, which you are more familiar with, are accelerating charges. So completely different attributes of matter make these waves. And that's all fine. Now let me tell you the bad news. The bad news is that space is extremely difficult to compress. It doesn't like to be compressed. And it turns out, and this is partly due to Kip, and mostly due to Kip, in fact.
I'm responsible for the stiffness of space.
Yes, you are. You're responsible for the stiffness of space. But no, you're responsible for the next statement, which is that it turns out that nature doesn't make very big expansions and contractions. Let me give you the numbers, and that's what Kip helped us with. It turns out, and I'll have to use exponential notation, and I'll try to describe it to you. It turns out that the maximum that you can ever expect nature to do, and I'm talking about accelerating masses that are the size of stars and that are zipping together at almost the velocity of light, even with that, you only get a change in distance over 4 kilometers. Take 4-kilometer distance. And the endpoints move by 10 to the minus 18 meters. What is that? That's 1,000th the size of a nucleus. Okay? So 10 to the minus 18 means a decimal point, 17 zeros, and then a 1, okay? That's a tiny, tiny number. And someone had to make a device that could do that. And that's where the other challenge came. And that's why, I guess, partly why we're sitting here. Isn't that right?
Yeah.
And that is that you had to now make a device that could measure such tiny motions. And that was there were 2 challenges there. It was done by doing the following technique, a very straightforward idea. The idea was to actually exploit the way I showed you what the gravitational wave does. It stretches in one dimension and compresses in the other. And what you do is extremely straightforward. You start in the middle, you send out a light beam, and find out how long it takes to go from here out to there and back again along, let's say, that dimension, and compare it with the time it takes light to go from that same point up and down. And you do this, and when there's no gravitational wave there, you make it so that the time is exactly equal back and forth. And when the gravitational wave comes along and does its stretching and compressing, it changes that time. Okay? And you measure that difference in time. That's the technique. And the trouble is you have to measure very tiny numbers. And so now it turns out that the part that was hard, and I'm almost there, the part that was hard was how to measure 10 to the minus 18 meters. And there were 2 problems with it. If you use light and use the wavelength of light one way, the wavelength of light is about 10 to the minus 6 meters. And you're measuring 10 to the minus 18 meters. So you have a factor of 1,000,000 times 1,000,000 smaller than the wavelength of light to measure. And the other problem you got is you got to make sure these points that you've labeled where the light goes back and forth don't jiggle much on their own. And that turns out the Earth's jiggling alone is just the fact that you are sitting here and the Earth is shaking a little bit. That's another factor of 1,000,000 times 1,000,000. So you have to develop techniques to do both of those things. So let me just finish. I said you had to develop techniques to do it with the measure, and you had to have techniques that made everything quiet enough. So that took 40 years. And just one more statement. That 40 years was an unbelievable experience for this country, because your National Science Foundation, the one that lives across the river, put 40 years and $1 billion into this of your money to get to what Kip is going to talk about in a minute. And the fact is they stuck with it for 40 years. And they had to stuck with it because we didn't know quite how to do those tiny measurements in the beginning. They helped us with that. We didn't really know what the sources were going to do, which Kip will talk about. And they even went along with this all the way for 40 years. And they stuck with it, and finally it worked this year, or in the last few years. So Kip, why don't you continue? That's what you want, right?
It was good. You did good.
Okay.
So I'm a theorist, not an experimenter. When I became convinced that Ray and his colleagues could really likely pull this off, and this was back in the mid-70s, I decided that I, as a theorist, should do everything that I possibly could to help them out. And so that's been my role as their theorist helper. The key thing that we understood in the early to mid-1970s was that the laws of physics say there are only 2 types of waves that can propagate across the universe, bringing us information about what's far, far away: electromagnetic waves and gravitational waves. Galileo started electromagnetic astronomy when he turned a little optical telescope at the sky and discovered the four moons of Jupiter. What we have done, and this was our goal going back to the early 70s, and Ray and I both laid foundations that go back to the mid-60s, so we both worked at it for 50 years. Our goal was to do with the other second kind of wave that you can have what Galileo did for electromagnetic waves. And the team of 1,000 people that Ray Weiss, or that Barry Barish, the third member of our triumvirate, that he designed, conceived, and put together, that team of 1,000 people pulled it off, building on the experimental foundations and ideas of Ray Weiss here, and others. So you know what has happened with electromagnetic astronomy since 400 years ago, since Galileo. We now have optical astronomy, radio astronomy, infrared astronomy, X-ray astronomy, gamma ray astronomy, all different wavelengths of electromagnetic waves. The same thing will happen with gravitational waves. By 20 years from now, there will be 4 different frequency bands of gravitational waves that are being observed and used to explore the universe. By 20 years from now, we will be exploring the birth of the universe and the birth of the fundamental forces observationally with gravitational waves. At the present time, what the LIGO team is doing is it has been exploring, discovering the collisions of black holes and how those collisions create a veritable storm in the fabric or shape of space and time, which emits these gravitational waves. And also have discovered collisions of neutron stars that produce not only the gravitational waves, but also electromagnetic waves. So you have multi-messenger astronomy with observing the same phenomenon with gamma rays, light, X-rays, radio waves, and gravitational waves, bringing us a whole new way to really explore phenomena that we understood somewhat vaguely until now. Now we understand ever so much better through these the combined observations of these types. And this latest discovery involved how many scientists on this? 1,000 gravitational astronomy and something like 2,500 electromagnetic astronomers. Yeah. And so this is taking off. And it was a vision. This is what we anticipated when we got started. But I must say, when Ray first described his idea for these detectors, and he was the primary inventor, I didn't believe it would work. And it took him and others about 4 years to convince me that it really could work, because it's so unbelievably difficult. The fact that this team of 1,000 people actually pulled it off is just admirable and amazing.
It is an admirable discovery. Thank you. I commented earlier that it is interesting to me. So I'm a neuroscientist by my own scientific background, and you know, gravitational waves was sort of something that they all talked about and occasionally tried to explain to normal people like us, and I couldn't fathom it. And now I think this is something that in our lifetimes is among the most startling discoveries and among the most important discoveries. And so for me personally, it's very exciting to be here, because this is an unbelievable accomplishment, as are each of them. Speaking of which, the next category is the Nobel Prize in Physiology or Medicine. They'll tell you what they did, but in my business, understanding these mechanisms that control the biological clock is another one of these sort of fanciful, esoteric things that could happen, right? You have this biological clock, and they'll explain. But think about it for a minute. It's sort of difficult to conceptualize that your body actually is independently telling time and taking care of you over time. Go ahead.
So I'm Michael Rosbash. I work at Brandeis University and am a Howard Hughes Medical Institute employee up the road a little bit. Biological clock. So at 4 p.m. this afternoon, when we're being taken back to the hotel in the van and everyone is going like this, that's the dip in midday alertness that is being controlled by the biological clock. And so this is a story that, for me, began in the early 80s, 82, a little bit earlier for Mike. I just leaned over to my colleague here, Mike Young, and said, when did you actually begin this work? I think in the early 80s, there was really a perfect storm of phenomena which came together, which allowed this work to go forward. On the one hand, there was the beginning of neurogenetics, that is, people, Seymour Benzer at Caltech and his student Ron Konopka and others interested in how the brain works and using genetics to explore this. And by genetics, I don't mean what's the difference between you and me, but the basic mechanisms as an inroad, as a strategy for getting at the mechanisms, the proteins, the phenomena which are actually governing different inborn traits, like a biological clock. And then recombinant DNA appeared at the same time, which allowed the field of behavioral genetics, which was a tiny bit esoteric, actually, because it couldn't reach out to other disciplines, to genetics, for example, to biochemistry, and allowed the field, and our two laboratories in particular, mine and my collaborator Jeff Hall at Brandeis on the one hand, and Mike and his people at Rockefeller on the other, to start to approach this problem by cloning, by identifying the gene, the one gene which had been identified, which gave rise to changes in the biological clock of all things fruit flies. And so the work that we did, and in watching the announcement from Stockholm and looking at what they decided what we did was important, this really went from 84, publications went from 84 to 98. We've continued after that, but I'd say those 15 or 16 years was the heart of the matter, when we were able to figure out, through really the efforts of our people in our labs, the 2 places, 3 labs, 2 places, that there is a feedback loop of gene expression, that is this original protein, which was identified by Konopka and Benzer, which our 2 laboratories cloned, that protein functions as a gene regulatory module, a transcription factor, and it's involved in shutting off its own expression. And that mechanism, with the appropriate time delays, which you need to generate to make an oscillator, that mechanism actually is at the heart of the clock, of the timekeeper. And so the molecules are synthesized, they go up, one of the products, this protein itself, the period protein, feeds back and turns off its own expression. The products decay, and when the levels get low enough, near zero, everything starts over again, and it takes 24 hours to go around the cycle, and that is the timekeeper. And so it's really a story of behavioral genetics. I was struck. So Ray Weiss and I live in the same town in Newton, Massachusetts, and I received a commendation at City Hall from the Board of Aldermen, and they said he was coming in a month. I never met him until today. But speaking of behavioral genetics, I suggest you go look up on Wikipedia his age, because he is a phenomenal example of behavioral genetics.
That old, huh?
We benefited from 2 phenomena, I think, which really gave our work particular prominence. One is, it turned out that exactly the same proteins and mechanisms that we had been studying in fruit flies, which you'll appreciate as a tiny bit esoteric, turned out to work in humans. So it's the same mechanism, it's the same proteins. In other words, it existed in our common ancestor 550 or 60 million years ago. There was a great grandparents that we shared with fruit flies, And that animal had the same mechanism which both branches have inherited. So that was fortuitous, luck. You need some luck, as you said, or the ambassador said. And so we didn't discover that, other people in the field did. And then secondly, it turns out that this timekeeping mechanism sits at the top of a hierarchy which governs more than half of the metabolism, half of all genes in mammals and humans are under the control of the circadian clock. So it's that simple. This little timekeeper is orchestrating more than half of the 25,000 genes or so that humans express. And that's why all of behavior, endocrinology, metabolism, everything, blood pressure, everything you can think of is undergoing circadian oscillations. And we had a little hand in that finding, that is the gene expression, the broad control of gene expression. But those are the two phenomena which took this fruit fly problem and gave it such prominence.
Thank you. That was great. Dr. Young.
So when I first became interested in this problem, it was actually the 1970s. I was a graduate student. And it seemed to be a problem in behavioral genetics. That is, how are genes related to behavior? And it seemed like Drosophila as a simple insect would be a great place, a manageable place to start. And I think what Michael alluded to that was not apparent at the time is this became a much broader question. So when Michael says at 4 in the afternoon you're going to go through a dip, that's a behavior response, but it's also a physiological response that's only sort of the tip of the iceberg. Almost every cell in our bodies has these clocks. Your livers have these clocks, your lungs, even your skin, which we have used to our advantage, has these little clocks running all the time, and they are essentially reflections, they're adaptations to the turning of the Earth. So they've been generated. There's a certain connection here between the larger universe. We have a bit of the larger universe in every one of our cells. And this has proved to be a tremendous advantage, not only of the little fly, but of course it's been retained, and we see it in ourselves. The running of these clocks is for different purposes in different organs. So the purposes, the genes that Michael referred to, the many genes that are regulated by these clocks, are not uniformly regulated in all of these parts of the body by these clocks. Clocks in different organs have different sets of genes that they're regulating with a rhythm. So that by the time you're finished counting up all the genes that are regulated around the body, it's about half of the genes that we hold in our genomes. So as Michael said, these clocks are not only ubiquitous, the clocks, the mechanisms that were worked out in the fruit fly over 20 or so years, and then with much more elaboration in another 20 years, this again going all the way back from me to the 1970s. These clocks are found in us in a fashion now that can be studied in tremendous detail. Because these clocks are more or less the same all the way from a simple fruit fly to a human being, we're now able, with information about the structure of the genome, to identify changes in these same genes because we know them, we recognize what they're doing. We can begin to study medical issues that are connected to misfunctioning clocks. And I'll just give you one example. So in the very recent future, just the past 2 years, we've been very interested in a syndrome called delayed sleep phase disorder. This is a disorder of sleep. Many people that show this disorder refer to themselves as night owls. You're up 2 or 3 o'clock in the morning tapping away on that computer, and of course you really don't want to get up before 11 o'clock or so the next day. And it turns out that about 1% of the world's population carries a single variation in one of these clock genes that will predispose them to having that kind of behavior. Somebody in this room is probably a carrier. Maybe some of you recognize the fact that you feel like a night owl. So this is important at a number of levels. One, it tells us that old terms like sleep preference are probably outdated. These kinds of things need to be rethought. Those individuals that carry this variation don't have a sleep preference. They have a genetic composition that indicates that they have a certain pattern of behavior. It's very important that we understand that. It's also very important that it's recognized and properly diagnosed. Beyond that, that's just one example, but with the current state of DNA-based information, we can essentially look at all the variation that's present in the human population and understand a great deal about heritable sleep and other disorders that are connected to the malfunctioning of these circadian clocks. These clocks certainly have an effect on something like a sleep-wake cycle, but obviously I think it's obvious if they're working in your liver, in your skin, in your lungs. There are many other manifestations that will have medical significance. So I think that the future holds so much more than the last 40 years, although the last 40 years have been very exciting.
Thank you. So I do have to say that I was at the National Science Foundation in the 1980s, and we were convinced you guys were going to get a golden fleece from Senator Proxmire about, you know, why are you supporting this stuff?
Which one? Which one of the things?
Huh? I'm coming to you. All of us. Because you may not be aware of this, but I was on the National Science Board during the funding of LIGO and something called Advanced LIGO. And I believe that there was a collective sigh of relief, not just admiration, but relief when you guys actually were able to see gravitational waves and we could go, psst, they do exist. We didn't waste. Never mind. Okay, thank you very much. Let's turn to Dr. Frank, please.
Well, all life functions in all our cells, in all organisms, really are constituted by the interactions of molecules. And in order to understand this, in order to understand diseases, in order to understand life processes, one needs to know the structure of these molecules and the way they interact. So how do we get information about the structure? For a long time, for decades, we got information, the best information from X-ray crystallography, which is a technique that was invented a long time ago, and then it was discovered it also works for proteins. And one gets a diffraction pattern, and from there one can synthesize an image of the molecule, and from that one can infer the atomic structure. So right now there are more than 100,000 structures in the public database, and they form essentially the basis of molecular medicine. That's why medicine is now essentially molecular, because we understand the function of so many molecules, including the ones that are implicated in circadian rhythm. However, there's a huge gap. It's a huge gap in all this research and in the database, which are molecules that cannot be easily crystallized. And so a long time ago, more than 40 years ago, I started working with electron microscopy as an alternative way of getting information about molecules. And this was very tedious. First, it was thought that molecules needed to be crystallized in order to get anything out of them with the electron microscope. And I was very stubborn in the belief that we can even get it from single molecules. Now, that was a very big hurdle, and many people thought I was really crazy to even try this. So first of all, we have to understand that electrons damage the molecules in the process. And so when you use enough radiation dose in order to get a clear image, you destroy the molecule in the process. So it required some kind of a thinking, some kind of an insight. How do we handle this situation? The idea is now simply that if we get molecules from the cell extract, we don't get one, we get 10, we get millions, we get billions of them. They're all identical copies. And if you have them in solution, they're all in different directions. They are randomly oriented. Okay, so instead of exposing one molecule in many, many different angles, why don't we just take an entire field of randomly oriented molecules and take one single very, very small intensity shot of these? Then we get all the information that we need for the three-dimensional structure. If we only know afterwards how the projections are related to one another. So I have solved the problem conceptually, but then I got myself in trouble with mathematics and computation. So all these years went into finding ways, mathematical and computational ways, on how to relate these different views to another, how to align, how to classify them into different subpopulations and so forth. So then there was this steady progress, let's say until 2012, where the method got more and more refined, and we got wonderful discoveries, but we never reached atomic resolution because there was a hurdle, and it turned out that the hurdle was the very poor performance of detectors. Film is the most popular detector. This is also not ideal, but nobody wanted to work with film, because you have to expose it and develop it and scan it into a computer. So you want to have electronic ones. First electronic ones that came about were CCD cameras. They were terrible. They were a fallback from film. And then all of a sudden, miraculously, 2012, a new kind of detector came on the market. $600,000, one of those cameras, which detect single electrons. So they have incredible resolution, incredible signal-to-noise ratio, and so it so came about that a technique that I've been developing, and my two co-laureates have been developing with me. That this technique all of a sudden could be propelled to the resolution of X-ray crystallography. And so with this huge gap, which involves membrane proteins, these are receptors, channels, many that are implicated in diseases, they all of a sudden can now be explored exactly as with X-ray crystallography. So this was the huge progress, and that's why there was all of a sudden a limelight on this development. Before, it was sort of it stopped at a resolution of something like 5 angstrom. So it was not enough to infer the atomic structure with high fidelity. And I have to say, as far as funding is concerned, I'm incredibly grateful for continuous, persistent funding by National Institute of Health. And then I was also a beneficiary of Howard Hughes Medical Institute until recently, until before the Nobel Prize was awarded.
It'll be interesting to see if Howard Hughes comes back. All right, and our behavioral economist. Could you explain to us, Dr. Thale?
Well, as they used to say on Monty Python, and now for something completely different. I should say that I was rejected for an NSF grant for fear of the Golden Fleece Award.
I wonder why.
So, you might wonder what behavioral economics is. And to quote a former economics laureate, Herb Simon, who was really a behavioral economist before the field existed, he said that the phrase behavioral economics appears to be a pleonasm. I'm quoting his, I don't know fancy words like that, but a pleonasm is a redundant phrase. And so why is it a pleonasm? Well, he said, what other kind of economics could there be? Presumably, economics is about the behavior of people in markets. So why do we need that adjective? And he answered his own question. He said the answer to that question lies in the assumptions of non-behavioral economics. So what are those assumptions? Essentially, and this will sound like a caricature, but it's not. Economists assume that people are very smart as the smartest economist, and have no self-control problems. They eat just the right amount and just the right things. They save for retirement perfectly. In fact, there have been 2 Nobel Prizes given for people who studied the theory of how people save for retirement. And Franco Modigliani most noteworthy. And the theory is that people figure out what they're going to earn over their lifetime, figure out how they want to smooth their consumption over their working and non-working years, what their life expectancy is, how much they would have to invest to achieve that optimally smooth consumption path, and then implement.
Wait, that's not true?
So that's the theory I learned in grad school, and it struck me as it had some problems. So I thought about maybe I should try and find gravitational waves. That seemed too easy. So what did I do? I began just by watching people and watching what they do. And it really all began with a list of funny behavior that my friends and colleagues exhibited. My version of Newton's apple, not that I would compare myself with Newton, was a bowl of cashews. So when I was in graduate school, I invited some friends over for dinner, and during cocktails, put out a bowl of cashew nuts, and people started nibbling rather ferociously. And I feared that our appetite for dinner was endangered, and so at some point I picked up the bowl of cashews and, while nibbling a few more myself, went and hid the bowl in the kitchen. And I came back, and since this was a group of economics graduate students, we immediately started analyzing what had happened. There's a lesson here about how many economists you want to invite to a dinner party. So the analysis came down to 2 points. One, everybody was happy, so they thanked me. Thank God you got rid of those cashews. And then the second point was that we weren't allowed to be happy, because a basic axiom of economics is more choices are always better than fewer. Because before we had a choice, eat cashews or not. Now we didn't have a choice. More choices are better. How is it that we can be happy? And so that's kind of where it started. My bit of luck was I met 2 Israeli psychologists, Daniel Kahneman and Amos Tversky. Amos, by the way, was one of those night owls. You wanted to meet with him. 11 was a good time to meet him in the office at PM. And they were doing, so Danny, of course, won the Nobel Prize 15 years ago. Amos would have shared it with him, but he sadly died at 59. And I guess the will has a stipulation that you have to be alive. That's the one thing that we've all managed to do, is live long enough. It's a key to winning this prize. So I met them, and they were doing work in psychology that had nothing to do with economics, but they had a finding, which, to summarize in one sentence, is that people make mistakes and that those mistakes are predictable. So economists had always recognized, they all think that that non-economists are idiots. So it's only in their models that people are so smart. But they comforted themselves in thinking that the mistakes that people make wash out, that they're mean zero. And so the aha insight I got from Kahneman and Tversky was that, no, these mistakes are predictable. And that was sort of the impetus. And so I spent a year with them exactly 40 years ago. So this is a 40th anniversary of my collaboration with Danny Kahneman. And let me leave it at that.
All right, well, thank you. So that was wonderful, and I actually wouldn't mind having them just go through again and do something, but we're not. It's your turn to have at them, as we say. And let me remind you, short, voice up at the end. Anybody want to practice? Do it with your neighbor next to you. If you'll raise your hands, we'll try to sort it out. There are people walking around with microphones. Can I suggest, before we do that, just to give everybody a breathing break, have a breath, look to your right, admire the view for a moment. There are people out there admiring the view. Okay, we're ready. Let's do it. Where shall we start? Okay, I think the woman near the window. You. But wait. Thank you.
This is for Dr. Rosbash. Please tell me about the daylight saving times. Are you for it or against it? I mean, I really... really would like us
All right.
a definite answer. Stop it.
This is like Cubs or Astros or something, right? So I think I'm mostly against it. The reason is because that 1 to 3 days after the change, especially in the direction where you lose an hour of sleep, is statistically dangerous. Car accidents increase notably, heart attacks. So strictly from a sleep deprivation point of view, and of course we as a society are sleep deprived as a baseline, and then when you add another hour onto that, it's problematic. So that's linked to circadian disruption. Of course, the other thing that happens in both directions is that there's a jet lag, a 1 hour jet lag problem, of course, because it's your clock is used to running on the time of Saturday, and Sunday morning after the clocks change, you've changed for an hour. So I think on balance, I think that's I don't see the advantages outweighing the disadvantages. And of course, the problem that we really should cope with is the fact that young people, on the whole, have a later, they're more night owls, if you will, than grown-ups. And so that is another problem to address, which some school systems are trying to deal with. Of course, the teachers and the workers are grown-ups and the kids are kids, and so you have two populations which have to get there. Anyway, so that's a long answer to your question.
So actually that relates to one of the Twitter questions that came in, which was, is there any truth to adolescents being difficult to wake up in the morning? Is there a biological mechanism?
Yeah, I think that is a fact statistically. So it's like everything. The mean for adolescents is later than the mean for older people, right? And so
More sleep.
And so
more sleep per 24 hours.
they simply they need more sleep. So there you are, right?
I like it. Okay. Where are we with the microphone? Let's go there. I'm just running around the room, so please don't be insulted.
This could be directed at any of the laureates, but maybe I'll stick with the folks from MIT and CIT. I'm curious to the key to a successful collaboration.
Can you put the microphone closer?
I'm sorry. I'm looking for the key to a successful collaboration between competitors. MIT and California Institute of Technology are seen as competitors.
You want me to do that?
Yeah, guys.
Yeah, look, let me try. The fact is that, let me tell you a little about MIT and Caltech. At the time when Kip and I met, MIT didn't think much of gravitational radiation at all. It was just too complicated, and people at MIT thought that there were no black holes, and there was, in fact, a very famous man who, when every time somebody mentioned him that X-ray astronomers have found something that looks like a black hole, he would then invent a wonderful, ornate description that was still physically possible, that avoided the black hole, okay? And that was the mindset at MIT. And if it hadn't been for Caltech, I don't think we would have ever gotten going. So it was a mutually, Caltech then actually did a very important thing. When Kip had already a very strong group going in relativity theory, in theory of gravity, Kip and I happened to meet once here in Washington. And we discussed all night long what might be a very good experimental group for Caltech to start with. And so it turns out in the end, what came of it was that they started a group with bringing Ron Drever from Scotland to Caltech. And it turns out that, yes, there was no problem between Caltech and MIT. We were working already together because of the individuals. See, all that competition you're talking about has to do with high-level nonsense, okay? What it turns out, I enjoyed Kip. I think he even liked me. And so we enjoyed the idea of looking at this field as a thing that we were going to grow together. And Ron, although he was difficult and a very brilliant man, but almost wrecked it for a while because of his personality. But it turns out that we overcame that also. There were many things along the way, but I would not call it a rivalry between Caltech and MIT. The problems that we had were that we were kids. And there were three of us, that was Ron Drever, Kip, and myself, and we tried to run a big project. And we couldn't do it. So finally we were told by people who were very august individuals, get yourself a single director. We got Robbie Vogt, and that was wonderful. He put the thing together. But then there was further troubles with Ron and Robbie, and we got finally Barry, and Barry actually, who didn't have emotional attachments to all things, he saw the thing very clearly, and there was no question that he is the one who put the thing together and made it happen. So it wasn't ever a rivalry between Caltech and MIT. I'm just trying to tell you, there were a lot of other problems, human problems, experimental problems, but it was not Caltech and MIT.
One other aspect that really needs to be emphasized was the whole thing was a hell of a lot of fun.
Yes, of course.
And it was collaborators, initially at 2 institutions, now at 90 institutions, who just enjoy working together on a common problem that is so very difficult that you have to collaborate to pull it off, and you get this enormous satisfaction both from the collaboration process and from the result in the end.
Let me just say, I mean, what he's saying is the absolute truth. And on top of that, it's the thing that makes it so you can live 40 years and with a goal that you don't necessarily worry about. Because every day is something interesting, you see? Yeah.
That's wonderful, actually, if you think about that. You know, we're in the House of Sweden, which has one of the per capita best scientific enterprises in the world. One of the Twitter people asked a question about international collaboration and how it played into the work of the laureates. I was just thinking that you guys actually from Massachusetts and California actually are an example of interplanetary collaboration. But anybody want to say anything briefly about international collaboration and its impact on your work? Please.
Well, I'd like to talk about a very, very good and close collaboration with someone in Sweden, with Måns Ehrenberg in Uppsala. And I think for me, for essentially bringing out the power of the technique, it was instrumental to have such a good biochemical collaborator. He was a world, or is one of the world's experts on translation, on the way the ribosome works, and so he was able to give me the purest and best characterized specimens that showed the ribosome in a particular state of functioning. And so this collaboration was absolutely amazing, and we probably got dozens of papers out of this in top journals.
Great. So let's go back to the floor. You. Wait, you need a microphone. Please say who you are.
Jim Dye, NIH. You mentioned the expansion and contraction of dimensional space, geometric dimensional. Is there an effect on time, the fourth dimension?
Yes, there is. I mean, it's a way of, and I said this to somebody privately today, there were a lot of misconceptions of how a gravitational wave actually does its dirty work. I mean, you can write it in 3 different ways. For example, you can think of it as a force, a tidal force. That's the way people thought about it earlier, as a force that actually pulls things like a tide does. You can think of it as affecting the clocks and not the space. And that happens in some experiments. That's the way to think about it. And you can also think about it of actually interacting with the light. The gravitational wave interacts with the light and puts sidebands on the light. It puts little things at different frequencies on the light. So there are all these different ways you can think about it. And all of them are right. Okay, this is the slippery part of general relativity. Okay? I don't know if you want to agree with me about that. That got us all into trouble. And it got Einstein into trouble too. There were so many ways of writing things in a coordinate-independent way, and sometimes Einstein himself got fooled, and he made some mistakes because of that. And it's hard to interpret some of the stuff physically in the theory. But yes, you can write the theory, or the experiment can be derived in all those 3 different ways, and they'll give the same answer. But you have to be careful not to do the following. Use half of one idea and with the other half of another idea. That'll screw it up to a fairly well, okay? Yeah.
Great, so I get a question.
Yeah.
Somebody did tweet it, but Dr. Thaler, you introduced a new word into some of our vocabularies, pleonasm. Close enough. So you got another word that you've been closely associated with, which is nudge, or nudge, depends. We of the Yiddish heritage, we do nudge. But do you want to say something about what that is?
Okay, so first let me point out that those are 2 different words.
Depends on where you sit. I can't quite say nudge. But which is yours?
Well, you just did. There's a footnote in the book Cass Sunstein and I wrote on about page 8. So
I missed it.
Get busy. Explaining the difference between the 2 words. So a nudge is a gentle push. A nudge is a pain in the ass.
That's a technical term, I believe.
Yes. Yeah. And you don't want to be a nudge. And too much nudging could make you into a nudge if you're not careful. So what is a nudge? It's some small change in the environment that attracts people's attention and alters their behavior. And we hope, whenever I sign a copy of that book, I always sign it Nudge for Good, which is a plea rather than an expectation. We didn't invent nudging. Firms have been doing it for years. And if governments do it, well, what we try to say is governments should do this in a way that will make people better off as defined by themselves. So I have tried in various ways to improve pension plans, and we're trying to get people to achieve what they will consider better outcomes, not what I think that they should do.
Great, thank you. Okay, back to you all. All right, back there.
Hi, Tamara Litwin, postdoc at the National Cancer Institute. I appreciated the story about the cashews. For the rest of you, how did you decide what problem was worth devoting 20 or 30 or 40 years of your career to?
That is a fabulous question. You got it?
Do. Yeah.
All right, who's on?
So I think there's, I'll try and answer that from my perspective. And I think that my own history doesn't quite have this glorious this glorious endpoint as a goal. When I was young, when I was your age, you're trying to you get into a field almost by accident. For instance, the same way many of us became a biologist, or you had a teacher who was inspirational and it became a role model, and you follow in that path. And then if you're a positive, optimistic person, and those kind of people enjoy what they do and generally create something good for themselves. So in my case, really, I think I didn't even know enough about circadian rhythms, frankly. I wasn't sure it was a real phenomenon because the underpinnings were sort of soft, but the experiments took you there. You know, so you you put one foot in front of the other and try to do something interesting. As somebody said, have a hell of a lot of fun and do something interesting every day. And it turned out that the observations dragged us in a good direction. Of course, that's one of, is the mic not working very well? That's one of several ways of describing the path. But you know, other people, these guys picked out, and maybe even Mike, they picked out something very long ago that was really worthwhile and a goal. But in my case, I don't think it's really an accurate description. We got there, but it was really more or less by accident. Midway through, we knew we were onto something good, but there was many years of just putting one foot in front of the other.
Yeah. Kip. So I would just like to repeat something in this connection. It was obvious that the outcome of gravitational waves would be fabulous for science, understanding the universe, if it could be pulled off. And so the central issue was, can it be pulled off? And that's where, at least in my case, coming in as a theorist, consulting with some superb experimenters, Rainer Weiss, Vladimir Burginsky in Moscow, I had to become convinced over a period of a few years that these guys really did have a chance, a good, reasonable chance of pulling it off before I was ready to commit. And so that was central, the central issue.
It feels very human. I like that.
Yeah. You want this mic back?
All right, let's go on this side somewhere, please.
Grab the mic.
So I can.
Oh, I'm sorry. Okay.
Yeah, a little different. I think this is working. Yeah, a little different perspective on the same problem. I had, as a teenager, I had encountered circadian rhythms. I grew up in South Florida. We had these odd plants in the backyard next door, and these blooms would open up at night and close during the day. And I thought, how odd! You've got a sort of a behavior in a plant. And many years later, there was a group out of Caltech that had isolated mutations that affected sleep-wake behavior in the fruit fly, Drosophila. And in fact, the original student that found those mutations tried to explain what he'd found to a Nobel laureate, Max Delbruck, at the time, and Delbruck shook his head and said, "No, this is impossible. It's just too complicated a behavior to be explained, to have a mutation of a single gene have an effect." So I'd been a postdoc at Stanford during a time when a new process of working with DNA, recombinant DNA. This was a wave that swept through genetics and molecular biology in the early 1970s and enabled work in spectacular new directions. And many of you that know something about that era understand exactly what I'm talking about. But coming out of that and starting my own laboratory at Rockefeller in the late 1970s, what I did was I just reached for, you could clone anything. You could work with any gene. It was, you know, the whole genome was there for you to explore. And so we looked at this problem and said, what's the most outlandish thing we can study? How about this behavior? It's behavior, it's genetics. There are all kinds of questions about the relationship between these two endpoints. And moreover, it was a behavior that had a quantifiability associated with it. There was the period length, which could be measured, very persistent. There were responses to environmental stimuli, such as you could put a 15-minute pulse of light on a fly and know exactly how its new behavior would occur the next day, much like giving a jet lag impact to an animal. So there was all of this quantifiability that made this not a fuzzy behavior, but a very precise behavior that we could look at in depth. So that was the original drive to work with something like this, both the quality of the phenomena that you could study, and also the tools that you could bring to it, and the fact that it was a big reach. And of course, we thought we were all alone at the time. Michael and Jeff similarly became fascinated with this problem. But as I think as Michael was indicating, as we began to dig into this problem, it just opened up and became much more, held much more amazing facets than, many more amazing facets than we had ever imagined originally. And so you just get reeled in to the problem. So you keep following it, and that's how you suddenly wind up on a stage 40 years later and realize you've been after this for a very, very long time.
Thank you. So there was a young woman here. Do you want to pass her the microphone? Thank you.
Hi, I'm Sarah, and I'm a postdoc at the National Cancer Institute. I just started my research career there, and I was wondering if you guys had any advice for somebody who's looking to hopefully stand in your shoes one day.
Anybody got any advice they want to stand by? Oh, I'm sorry. I didn't mean to modify the question.
Well, my advice would be to, if you have a splendid idea and everybody disagrees with you, just persist. Just go on.
Yeah, that's the way to do it.
That's one of my favorite answers of the day. All right, who can top that? Somebody here, please.
Hi, I'm Peter Young with George Mason University. Should NASA invest in a gravitational wave observatory?
Yeah, I'll gladly talk about that. In fact, they are. And as Kip said earlier, when he was talking about the spectrum of gravitational waves, the ground-based thing that LIGO does sort of look at events, looks at phenomena that are between a sort of period of 1/10 of a second to maybe 10,000ths of a second. So between 10 to the minus 4 to 10 to the minus 1 second. And NASA and Europe together, ESA and Europe, this is almost as long a project as LIGO, have been thinking about and looking very hard at the problem of making a triangle in space, a triangular, equilateral triangle in space, which has arms that are 1.5 million kilometers on the side. And that's called LISA, L-I-S-A, the Laser Interferometer Space Antenna. And they will look for all sorts of other effects that have periods of some numbers of hours to minutes, completely outside the band of what LIGO can do. And that includes the kind of black hole that lives in the middle of our galaxy. And when it eats something, it'll make a very slow signal and a very persistent signal that you can see for a while. It'll even see the gravitation radiation from white dwarf stars in our own galaxy. So it's a completely different kind of phenomena. So they are planning that, and that is now scheduled, and the NASA got out of it for a while, then they got into it again, and now they're planning it together with the Europeans. And I hear numbers like 2030, 2032, some people say 2038 when this thing might get launched.
It's worth emphasizing that the ratio of wavelength of the waves that LISA would see to those of LIGO is about 10,000. And that's the same as the ratio of radio wave wavelengths to optical wavelengths. So LISA is the analog of radio astronomy if you think of LIGO as being like optical astronomy. And when you recognize the enormous difference in what we learn about the universe with radio telescopes versus optical telescopes, it's the same story here.
Great. Okay, ma'am.
In-Shi Chen, postdoc at NIH. I have practical questions. So, do you have any good suggestions to cope with jet lag, particularly after long hours traveling? Thank you.
Is this working? No.
No.
Before answering your jet lag question, is this on?
Yeah, I think it's
there we are. I wanted to just return to, since you're the third postdoc who asked a question, although less more practical than the other two. I did want to make one overarching comment, something I alluded to before, but perhaps didn't say it directly. I think prizes confuse the means and ends aspect of work and of science. And I think, how could we stand in your shoes? I mean, I never would have ever done this for a job with thinking about that. It was totally unexpected. And if we had to do it all over again, it never would have happened, right? It's a statistically super improbable event. And so what we do working in the lab at the bench is a craft. And you've got to really like doing experiments. You've got to take a lot of pleasure in the daily activity. Exactly. And that is what sustains you in the work, not a great discovery. And without that, you're in the wrong business. And so that's the, that's
great advice. I like that. I think we have time.
And now jet lag. Oh. So I am an incredible sufferer of jet lag. I have never found anything but drop-dead sleeping pills to the same thing that everybody else takes. And I've tried everything else myself, melatonin, et cetera, nothing works for me, and I suffer, just like you. So I think that there's, there are biotech companies that are working on this, of course, and some of them are attacking the very genes, one in particular that Mike's lab discovered. And so I think there's hope there, but
for her, not for us.
Right.
Actually, having just met you, I think you should speak only for yourself.
That's great. I think we have time for 2 more questions. So, okay, you be one. There, you, the guy now standing up. So the mic, you. Yeah, the guy looking around. Yeah, that you. If you stand up when I wave in your general direction, the odds are higher. Hit it.
All right, thanks. I'm David Fenigstein, a PhD dropout. But this question is for Dr. Weiss and Dr. Thorne. So one of the things that you spoke about is after the success of LIGO, you've started to have a much greater understanding of some of the phenomena in the universe. I was wondering if you could expand on, say, one specific thing that we understand now that we just had a vague understanding of before.
Can I do that, or would you want? I think both of us should do that.
Go ahead.
But let me give you an example. And this is, to me, I mean, I'll tell you, when people ask me, how did you feel when we finally discovered the gravitational waves from a binary pair of black holes going around each other? And the thing is that what was so spectacular about that was 2 things. First of all, we found out that black holes live in pairs. We didn't know that. We didn't know that they lived in pairs. In fact, we couldn't predict how many we would ever see because we didn't know that. We could guess at it, but we couldn't use it as a basis for design. The other thing is that the waveform that we saw, and this is something that Kip is very proud of, and he should be, is that it was finally possible, by the time we got to the point of making that discovery, that people were able to solve the Einstein field equations, those very complicated equations, that in such a way with a computer, and also with analytic methods, but mostly with computers, that you could compare directly what the Einstein theory said with the waveform that was measured. And it was a pretty damn good fit. And the thing that's so amazing about it, to me at least, and Kip will have a different answer, or a different viewpoint maybe, is that here's this theory that was made up all in here, in the tuchus, right here, okay? And, and what happened is that, sure, there were some facts, but not very many. And Einstein had it right. And he had it right over a dynamic range of gravity, which is so enormous, a factor of almost 10 to the 14. In other words, strong gravitational fields. This is about the strongest one we ever experienced, was the one, that black hole. And also the kinds of things we've been doing for years, measuring weak gravitational fields. The theory works over that fantastic dynamic range. That was really spectacular. But you probably have a more profound way of saying this.
Well, I would just elaborate.
Yeah.
And for me, so the neutron-star collision has made a lot of press lately, but I like the black hole collision because as a result of the computer simulations, which were done near the time, with just a couple or 3 years before the observation. For the first time, we saw how warped space-time behaves when it is highly nonlinear and highly dynamical, when it's behaving like the surface of the ocean in a giant storm with crashing waves. And we see that in the simulations, and the comparison of the observations of the wave shapes with the theory says that really is what happens. And so we didn't know how warped space-time behaved in the storm until just a couple of years before the observations. We now have both the theory from simulations, and we have the observations that say that really is what's going on. And that, to me, is just a fabulous insight for the first time understanding this phenomenon.
That's great. Okay, last one.
Manjuli Bamzai from the National Science Foundation. Congratulations to all the laureates. And Alan Leshner asked us not to be distracted with what's happening outside. But I couldn't help but notice that, we're seeing senescence and then we'll be going to winter. So my question is, what's the connection between the circadian rhythm, which is like 24 hours, and the seasonal rhythm, if any, in terms of evolutionary processes?
Sure. So there are relationships between these. It was shown many years ago that, for example, in animals that are very seasonal in their reproduction, they have to have a way to measure day length, that is, opposed to night length. In order to measure day length in a useful way, though, you have to have something to compare it to. And so they compare it to their circadian clock. So if you have a way of reliably measuring 24 hours, whether or not the world outside seems to be changing, then if you now count the number of hours, effectively this is what they're doing, if you now measure the number of hours of daylight against that 24-hour constant, then there will be thresholds where the day length will either be shorter or longer than that threshold, and that will stimulate something like reproductive competence. So there are ways in which this is done. There's still a great deal of mystery about those connections, but what has been clear in many different experiments using many different organisms is that the circadian clock winds up being the constant against which day length is measured.
So this has been fabulous. I love this. Okay, I'm going to ask you for 2 more sets of applause. First, congratulations to the laureates. And secondly, I'd like to thank the ambassador and her colleagues for their hospitality and for organizing this. Okay, what happens next?
Well, I just want to thank you for being here and asking so many interesting questions, and thanking you for letting us pick your brains. It's been very stimulating and very good. And I just want to wish you welcome back next year, when I hope that we have American Nobel Laureates. I can almost put my hat on it if I had one, that there will be some. It always happens. So we are very happy that you were here. Please continue to follow our work. And do come and visit us again. Our embassy and this building is open for exhibits, seminars, music, theater. So look at our program, and please do come and join us again. And thank you so much for being here. And, of course, last but not least, to thank Alan. And I hope you will be back next year as well. Thank you so much.
When you see them, you will realize why I love my sweet rain. When it's raining, I know it's the sun. Cause it's in my baby's smile. And I think that I'm the lucky one.